In this Part 2 video, as in the previous Part 1 video, we continue our study of the two foundational models of economic growth. Earlier, we focused on the Harrod-Domar model. Now, we turn to the Solow Growth Model. Let us briefly summarize what we already know. The Harrod-Domar model predicts instability, while the Solow model predicts convergence. Recall the key variables and parameters that form the building blocks of growth theory. Y of t and K of t denote total output and total capital stock of an economy at time t, both measured in units of currency. Both of these aggregate macroeconomic variables change over time. We write y dot to represent the derivative of output with respect to time, and k dot for the derivative of capital. These represent instantaneous rates of change of output and capital. When we divide y dot by y, we obtain the growth rate of output. Similarly, k dot divided by k gives the growth rate of capital. When multiplied by 100, these ratios become percentage growth rates. These growth rates form the foundation of all growth theory. Both Harrod-Domar and Solow begin from the same fundamental accounting identity. The change in the capital stock per year equals new investment per year, minus capital that wears out per year. The lowercase letter s represents the saving rate out of national income, and the Greek letter delta represents the depreciation rate of capital. Up to this point, both models are identical. From this common starting point, however, the two models diverge sharply, because they explain economic growth using very different mechanisms. The Harrod-Domar model assumes a very simple production structure. Output depends only on capital, while labor and technology are taken as fixed or ignored. This assumption implies a fixed capital output ratio and no substitution between factors of production. As a result, Harrod-Domar predicts that the growth rate of output is fixed. Solving the Harrod-Domar differential equation shows that output grows exponentially at a constant instantaneous rate, known as the warranted growth rate. If actual growth equals this warranted rate, the economy stays exactly on its growth path. But if actual growth is even slightly higher, output diverges upward. If actual growth is slightly lower, output diverges downward. There is no stabilizing force that pushes the economy back. This property is known as knife-edge instability.
Now let us turn to the Solow growth model. The Solow model assumes a neoclassical production function. The particular functional form we use here is the Cobb-Douglas production function. Output depends on capital, labor, and technology, with diminishing returns to capital. The uppercase letter A represents the level of technology. It measures how efficiently capital and labor are transformed into output. Technology has no natural physical unit of measurement, and is observed indirectly as total factor productivity. What matters in growth theory is not the level of A, but its rate of growth. The parameter alpha represents capital's share in output. It lies between 0 and 1 and measures the percentage increase in output resulting from a 1% increase in capital, holding other inputs constant. To simplify the analysis, we express all variables in per effective worker terms. That is, we divide output and capital by the level of technology and the size of the labor force. This transformation removes scale effects and allows us to focus on capital deepening. In per effective worker terms, output equals capital raised to the power alpha. This simple relationship is the core of the Solow model. As in the Harrod-Domar model, we begin with the capital accumulation identity. The change in capital equals investment minus depreciation of the existing capital stock. In the Solow model, however, we transform this identity into per effective worker terms. Output is expressed per effective worker, and capital accumulation is adjusted for capital dilution caused by population growth and technological progress, in addition to depreciation. Therefore, in the Solow model, capital accumulation reflects two opposing forces. Investment increases capital per effective worker. But depreciation, population growth, and technological progress all reduce capital per effective worker. Population growth dilutes capital across a larger labor force, while technological progress dilutes capital across more effective units of labor. After accounting for these forces, we obtain the key nonlinear differential equation of the Solow model. The change in capital per effective worker equals saving times output per effective worker minus break-even investment. Break-even investment has three components: depreciation, population growth, and technological progress. Next, we define the steady state. A steady state is a situation where capital per effective worker is constant over time. This means the change in capital per effective worker is equal to zero. Setting the equation equal to zero does not mean the economy stops growing. It means that saving-based investment exactly offsets depreciation and dilution. At the steady state, investment equals break-even investment. This condition defines the long-run equilibrium of the Solow model. We now solve algebraically for the steady-state level of capital per effective worker. The steady state depends positively on the saving rate and negatively on population growth, technological progress, and depreciation. Once steady-state capital is known, steady-state output per effective worker follows immediately. Output is simply capital raised to the power alpha. At this point, it is important to connect this steady-state analysis to the underlying dynamics. Capital per effective worker evolves according to a nonlinear differential equation. Solving this equation analytically requires advanced calculus, specifically the Bernoulli equation technique, which is beyond the scope of this lesson. However, the general solution has an important implication. The solution contains an exponential term that depends on time and the initial level of capital. As time goes to infinity, this exponential term vanishes. When it vanishes, capital per effective worker converges exactly to the steady-state level we previously obtained by equating saving-based investment with break-even investment. This shows that the steady state derived algebraically is fully consistent with the dynamic behavior of the Solow model.
Now let us illustrate the Solow model using a numerical example. We assume a Cobb-Douglas production function per effective worker. The saving rate is set equal to 20%. The capital share, alpha, is set equal to 0.3. Population growth is 1% per year. Technological progress is 2% per year. The depreciation rate is 5% per year. Together, these forces imply that 8% of capital per effective worker must be replaced each year just to keep capital per effective worker constant. Using the steady-state formula, we compute the steady-state level of capital per effective worker. The result is approximately 3.7 units. This is the long-run level toward which capital per effective worker converges. Substituting this value into the production function gives a steady-state level of output per effective worker of approximately 1.48 units. When the steady-state level of capital per effective worker is substituted into the expressions for saving per effective worker and break-even investment, both are equal to approximately 0.296 units of currency. Now consider the graphs. Investment per effective worker is upward sloping but concave, reflecting diminishing returns to capital. Break-even investment is a straight line through the origin. Their intersection determines the steady state. We can now verify visually what we determined numerically. At the steady state point, measured in units of currency, capital per effective worker is approximately 3.7. Saving per effective worker equals break-even investment at approximately 0.296. And output per effective worker is approximately 1.48. If the economy starts below the steady state, investment exceeds break-even investment, and capital per effective worker rises. If the economy starts above the steady state, break-even investment exceeds saving, and capital per effective worker falls. In both cases, the economy moves toward the same steady state. This adjustment occurs from both directions. This is why the Solow model predicts convergence. In contrast to the knife-edge instability of the Harrod-Domar model, the Solow model contains an internal stabilizing mechanism. Growth continues through technological progress, but capital deepening eventually stabilizes. This stabilizing force is what makes long-run convergence possible.